So now exercise 6. If A is a finite set having n elements, then we have to prove that A has exactly 2 to the power n distinct subsets. So this is actually nothing but the number of elements in the power set of A. So we will now prove this by induction on n. When so let us start off by mentioning that we are applying induction on n. When n is equal to 0, that means when A is the empty set, that is when A is the empty set, the only subset of A is the empty set itself, because the empty set is the only subset of itself. So in this case, the number of distinct subsets is 1, which is nothing but 2 to the power 0, and you can see that here in this case n is equal to 0. So when n is 0, the claim is true. So the result is true when n is equal to 0. Assume that the result is true for some non-negative integer n, and that just means that if a set has n elements, then it has 2 to the power n distinct subsets. That is, any set having n elements has 2 to the power n distinct subsets. Let B be a set having n plus 1 elements. Okay, and now we have to prove that the number of subsets of B is 2 to the power n plus 1. That's what our aim is, and this assumption is our induction hypothesis. Now we have to carry out the induction step and prove this. Note that even when n is 0, n plus 1 is a positive integer. So that means the set B we have chosen here is non-empty. It has at least some element. So we can choose one element. Choose an element x belonging to B. Then this difference, if we remove this element x from B, this set has how many elements? N elements. Right. Now by the induction hypothesis, that means this assumption, the number of distinct subsets of this set is, since it has n elements, so according to our assumption it will have 2 to the power n distinct subsets. Okay. Let C be any subset of B. Now we are not really interested in just the subsets of this B minus x, but we want to know about all the subsets of B. So let C be any subset of B. Then exactly two cases arise. Either x belongs to C or x does not belong to C. If x does not belong to C, then since C is already a subset of B, now if additionally x is also not in C, then C is a subset of B minus x, and the number of such subsets is 2 to the power n. So there are 2 to the power n subsets of B that do not contain x. The other case is when x belongs to C. On the other hand, if x belongs to C, then okay. Now if x belongs to C, then from C also we can remove x. then C minus X will be a subset of B minus X, right? From the induction hypothesis, the number of such subsets C minus X is, again it is 2 to the power n, because after all this is a subset of B minus X, right? Now note that any subset of B which contains X gives rise to one such subset of B minus X. That is, if C is a subset of B that contains here, where have I written? C is a subset of B that contains X, then C minus X is a subset of B minus X. So we are getting 2 to the power n subsets of B which contain X. Do we have anything additional? No. Why? Because you see, if we get anything additional, any other subset of B that contains C, then that would create more than 2 to the power n subsets, which is not possible according to our induction hypothesis. Hence, the total number of subsets of B is it will consist of those subsets that contain X and those that do not contain X. Those that do not contain X are 2 to the power n in number. Also, those that contain X are 2 to the power n in number. So the total number of subsets of B is 2 to the power n plus 2 to the power n, which is 2 times 2 to the power n, which is equal to 2 to the power n plus 1. And this completes the induction hypothesis because we have n plus 1 here. Oh sorry, I said induction hypothesis. This completes the induction. And also the solution, sorry. Okay, so this was the 6th exercise. Now the 7th one. A survey shows that 63%, this is the type of problems that you see in a school book. Nevertheless, it's also a problem and we should be able to solve it. Of American people like cheese, whereas %76 like apples. What can you say? about the percentage of American people I need some ink before I can say anything about the percentage. That like both cheese and apples. The given statistics are not meant to be correct or meant to be accurate, I think. Yeah. It's not accurate, it's just for the sake of the problem. Okay. So to solve this problem, we have to first of all define some sets that represent these parts of the American population. So, but before that, let the size of the American population at the time of the survey be n. This is definitely not something that is constant. It changes. People are born, people die. So it changes, but at the time when this survey was conducted, there was some size, and that size is taken to be n. We note that we don't know what n is, and we won't need to know. Okay. Let A be the set of American people who like cheese, and B be the set of American people who like apples. Then it is given that 63% of the population likes cheese. That means number of elements in A is do you see why? Total is n, 63% of that is this, and like that 76% like apple. Okay, Now this problem may trick you into thinking that A union B is everything. That is, A union B is the entire population. But that is clearly not true, because A has those people that like cheese, B has those people that like apples. But so A union B, that set has those people that like either cheese or apples or both. But there may be some people who neither like cheese nor like apples. So the total population is actually bigger than A union B. Okay. So, and we don't really know the size of A union B. The only thing we know about that set is that it is the number of elements in A union B is at most n, because n is the total size of the population. So we have n is greater than or equal to order of A union B. Okay. And by the fifth exercise that we have done in the previous video, we know that this is equal to order of A plus, or order I am saying it just means number of elements, okay, nothing else. Okay, so this much is understood. Now this is equal to 63 divided by 100 n plus 76 divided by 100 n minus order of A intersection B. This implies after some algebraic manipulation, you see that if you take it on that side, bring n on this side, then you will have this is greater than or equal to 63 by 100 n plus 76 by 100 n minus n. Okay, and the right hand side is equal to, what will it be? 6 plus 3, 9, 39, because we have minus n, 139 minus 100, so 39 divided by 100 n. So our final conclusion is this. Hence, at least 39% of the American people like both cheese and apples. Okay, at least 39%. It may be more than that also. Right. Then exercise 8. Given two sets A and B, their symmetric difference is defined to be A minus B union B minus A. So it involves both the differences that can be formed using A and B. So that's why it is named as symmetric difference. Prove that the symmetric difference of A and B equals this set A union B minus A intersection B. So the solution goes as usual. We show that each one is a subset of the other, and thereby we will have equality. We start off with this set, the symmetric difference A minus B union B minus A. This implies X belongs to A minus B or X belongs to B minus A. Let me again repeat that OR is inclusive OR. Okay, in mathematics, whenever you encounter OR, it is inclusive OR. That is, either something is true or something else is true or both are true. If you want to use exclusive OR, you have to specifically mention that. So the fact that both of these statements can be true is included in this. That is understood. Now this means X belongs to A and X does not belong to B, or X belongs to B and X does not belong to A. Okay. Now either this is true or this is true, right? If this is true, then X belongs to A and X does not belong to B. If this is true, then X belongs to B and X does not belong to A. So that means either X belongs to A or X belongs to B. Or if you find it difficult to think of it like this, we can use the principles of mathematical logic and write this statement like this: X belongs to A. Okay, what will it be? Should I write? Okay, yes, yeah, I can write it like this. This or X belongs to B, and see, when the structure of a compound statement like this becomes really complicated, you will get confused. There's high chance that you will get confused what to write next, and whatever you write next, whether it is true or not, you will have confusion. So it's better to use the principles of mathematical logic, like the distributive law, associative law, for statements and their logical connectives like and or. For example, here we have and, here we have or. What to do after this? I am now using a distributive law, okay, where or distributes over and, this or this, and again this or this. So that those things are available in my videos on mathematical logic. You can go watch them. So it's better to use them instead of just vaguely thinking of the whole situation and coming up with something wrong. Okay. So this and x belongs to A and x does not belong to B, or x does not belong to A, then we have to further work with these two things. Okay, now here again I can use distributive law. Or distributes itself over n, but now from this side. Actually we can take it on that side also, but it will make no difference. So here I will write x belongs to A, or will go inside and the two statements will be separated by and. That's what distribution means. Or x belongs to B, and x does not belong to B, or x belongs to B. So this is one thing, but it's not all. We still have to write and just like that with this second one, x belongs to A, or x does not belong to A, and x does not belong to B, or x does not belong to A. Okay, so the first one, this just tells us that x belongs to A union B. And now what about this one? X does not belong to B, or x belongs to B. This is always true. Okay, in fact that also follows from a statement in mathematical logic that is known as I think the law of exclusive middle. This is always true. So whatever happens, this is true. So there is no need to write this, because it is whether you write it or not. If you write a universally true statement with something else, that is not going to affect the situation. So we can discard this, because this is always true. So what I am trying to say here is that since this is a conjunction and this and is true, if both this and this are true, since this is always true, so the truth of this conjunction now depends entirely on the truth of this one. So this determines whether the whole thing is true or not. So that's why that need not be written, this part. Okay, just like that this one need not be written, but there is an and in between, keep that in mind. And okay, now what about this one? X does not belong to B, or x does not belong to A. So either x is not in B or x is not in A. Do you think it is possible for x to be in A intersection B? No, because if x belongs to A intersection B, then x will be both in A as well as in B. This or this means one of them must be true. If this is to be true, then one of them must be true. So if x does not belong to B, then definitely x cannot belong to A intersection B. On the other hand, if x does not belong to A, then also x cannot belong to A intersection B. So this implies x does not belong to A intersection B. Finally, this conjunction or this and implies x belongs to A union B minus A intersection B. Okay. Hence, the symmetric difference is a subset of this set. We will now prove the opposite containment. Next, let instead of writing let, we have suppose we are taking an element y in the second set, then this implies it's confusing to not have the dividing line. No? Let me just draw it. This anyway we had to rub off, so let's get rid of this. Okay, so now this implies y belongs to A union